All right, so we want to find the derivative of this function, and there's a lot of things going on here. We have a reminder that the sine squared written this way is the whole sine times itself. And so that's important to know. So we have a bunch of functions here. Let's copy that. Gotcha. So we want the derivative with respect to x of this right here. And I mentioned when we're doing functions like this, we should identify the order of operations here in order to determine which is the inner, which is the outer. So considering the order of operations, if somebody gives me an x value, right, given x equals whatever, what am I going to do first here? Well, the first thing I'm going to do is I'm going to raise it to the 6th power. So I'm going to take -9 times whatever x value I was given and raise it to the 6th power. I'm going to make that calculation. What's going to happen next? Second thing that's going to happen is before I can square, I've got to figure out what the sign is there. So the next thing is, what is the sign of that answer above? Once I know the sign, then the third thing that's going to happen is I get to square whatever I found from above. Okay, so that means this, and then multiplying by -5, you could consider that a fourth function, but remember, multiples just get pulled out. So I'm not even going to think about that as a function, even though it is. So let's see. So this is my inner, right? This is definitely the last thing I do, the outer function, and then we have this middle function here. And I need to know what each of their derivatives are. Because the chain rule says find the derivative of the outer function, multiply that by the derivative, in this case, of the middle function, if I could spell middle, go. And then multiply that by the derivative of the inner. So we did an example kind of like this in class the other day. So it turns out if you have a composition of a composition, it's just this chain of multiples, which is kind of cool. So for the derivative, first, consider the outer function, and the -5, I'm just going to attach that on the outside. So we get the -5 just chilling there. Derivative of a square is 2 times whatever you squared and drop the power by 1. So I'm just going to write it that way. What happened to be inside? What was I squaring there? Well, I was squaring the sine of -9x to the 6. So I put everything else back in. Times the middle. The middle is the sine, so derivative of the sine is the cosine of whatever. That's it, that's its derivative. What happened to be inside there was a -9x to the 6th. And then finally, we multiply by the derivative of the inner, -9x to the 6th. So that's going to be a -9 times 6 times x to the 5th power. So again, outer derivative is here, right? The 2 base to the power 1. Middle derivative, that was the derivative of the sine, that's right there. And then the inner is right there. And then I clean this mess up. All right, so we got a 5 times 2, which is 10, and a 9 times 6, which is 54 on a good day. And a negative times a negative is a positive. So I think I'm getting 10 times 54, so 540 out front. And then might as well bring the x to the 5th out front. I don't know why not? And then we have a sine times a cosine. So sine of -9x to the 6th times the cosine of -9x to the 6th. Did we get everything? So let's see, we got the negative times a negative, 5 times 2, 9 times 6, that's covered. We got the x to the 5th covered. We've got the sine and the cosine. Yep, got everything. So I always like to go back through in these complicated ones, make sure I've got all the pieces right. Nice. And then does this simplify it all? Sine times cosine, there is a product rule for that, but I don't think that's going to make our life any easier. Maybe it will. Let's think about that for a second. Could I use less ink on this? We need trig tables. I think I'll grab the one from our book. I think I can use less ink on this one. A little voice in the back of my head saying, yes, yes. That's the double angle formula right there. So let me see, online book. So you might want to have a table of trig identities handy. So where was that? That was in Review of Precalculus in the back of the book. All right, so I'm thinking that looks like the double angle, one of the double angle formulas to me. All right, yeah, sine of 2x is equal to twice sine times the cosine. So I think I can apply that here and use a little less ink. All right, so I'm just going to write that formula down and to figure out how to apply it. So the sine, I'm going to use a different variable. I'm going to say the sine of 2u is equal to twice the sine of u cosine of u. And so for me, the u is that negative 9x to the 6th, right? That hung out each time. So then 2u would be the sine of negative 2 times that, so negative 18u, no, negative 18 x to the 6th. So I'm just replacing, my claim here is that u is negative 9x to the 6th. So 2 times that. And then on the other side, I need a sine, a cosine. So I got my sine times my cosine, and then I need a 2. So I'll have to pull a 2 out of the 540. So that would be, what's half of 540? That would be 250, 60, 270. So that's 2 times 270. So I need that 2 also. So I think I can also write this as 270 times x to the 5th times the sine of negative 18x squared. Oh, that 18x to the 6th. That's a lot less ink if I'm correct. And I think I'm correct. Let's test it. Okay, so the test is we have 2 options. We can whip it into that derivative calculator thing. And if you haven't been playing with that, you should. However, it even shows the work. I hate to show it, but it's a beautiful thing. What the hell, why not? And then we'll test it by making a tangent line. So derivative calculator. Just plug in your function, -5, and you got to enter it in a way that it can read it. So that can be sometimes tricky. So I'm going to do parentheses, sine of -9 x raised to the 6th, and then close the sign, and then I wrap the sign in parentheses so that I can square it. And then it rewrites it down here. So that looks correct. And then I just hit go, and then it will run its algorithms on it, which is kind of like what I just did. It says, oh, we got a chain rule. And then it'll probably also notice the double angle formula there. Oh, it didn't. Huh. Oh, it's got another simplify button. So then it'll apply some algebra to that. But if you just rely on this for your homework and don't write the steps down yourself on the exam, you're going to be in deep shit. So please write stuff down. Oh, it's got a negative and I didn't. What did I mess up? Huh. Okay. Oh, I forgot my -9. Is that what I did wrong? To -9. What did I type in? Oh no, I typed the -9 there. So it thinks it should be -270. All right, let's look back at my work. Did I make a mistake? Otherwise, that looks like what I had, except for the negative. So the -5 is hanging out front. So that's just hanging. That's fine. There's a multiple. Derivative of, let's see, the outer is just 2 times that. That's okay. And then the derivative of the sine is the cosine. And the derivative of -9x to the 6 is -9 times 6x to the 5th. And so I have a negative times a negative. Anybody see what I'm missing here? And then we multiply those together, right? Interesting. Maybe the derivative calculator is wrong, but that's unlikely. That thing's programmed pretty well. Multiply outer derivative, middle inner derivative, negative times negative is a positive that they claimed. Oh shit, I see it now. All right, check this out. Notice that I have a negative right here on the 18. And in their answer, they do not have a negative inside. So our answers are actually the same. And here is why. Do they have this identity here? Yeah, the sine of a negative angle is the same as the negative sine of the angle. So they applied that identity and I didn't. So my answer is equivalent to theirs. They have the negative on the outside, I have the negative on the inside. No big whoop. All right, so next, one last test of this thing. I am going to see if this graph's okay. GeoGebra. So we're going to make a tangent line. So let's write down what we're going to do next. Check with a tangent line. This is good practice because you guys need to be able to find tangent lines at x equals, what do I want x to equal here? I guess it doesn't matter too much. I think 1 should work fine. So let's graph x equals -5 parentheses sine of -9x squared, no, to the 6th. Oh, not 26th. Oh, and it's having a hard time graphing this. This is a tough one. Come on, keep up. Come on, GeoGebra, you can do it. What? You're stuck. Uh-oh, I think I broke GeoGebra. This is too much fun. Really? You froze on me? Ah! Can't do anything to break it. Oh! Oh, there we go. It's catching up. It's having a wicked hard time calculating this, so I think we might be out of luck. All right. Wait, I wonder if Desmos can handle it any better. All right, let's try Desmos. Could be we've exceeded the ability for these computers to calculate. Oop, wrong Desmos. Desmos. All right, let's try here. I bet we're going to lock up Desmos too. I don't think it's going to do any better. -5 parentheses sine parentheses -9x raised to the 6th. Oh, okay, it's doing better. Close parentheses, and square it. Wow, okay, so this is cool. Desmos outdid GeoGebra here. And then let's zoom in there because it gets a little messy. The thing is with the 6th power, the period is increasing as we move out, or decreasing, I should say. So let's configure this to go from like -1 to 1 might be safer, be less messy, out in the fringes. Oh yeah, that's cuter. All right, and then let's go for a derivative at 0.6 here. So we want the point 0.6, comma f of 0.6, bang. And we think the slope function is, I'm going to go with my version, which was 270 times the times x raised to the 5th times the sine of negative 18 x raised to the 6th. Okay, type that right. And I don't really want to see that. I just want to use it. All right, so that should be my slope function. So I'm going to say m, my slope at that point is the derivative, plug in 0.6. Negative slope, that's good. That's definitely a negative slope there. And so then the tangent line should be y minus f of 0.6, right? Y minus y1 equals m times x minus x1, 0.6. Sweet, look at that. Nailed that tangent line. Yeah, so it looks like we do have the right slope function. It's a slightly different version of the function than came up with in the derivative calculator. And I do expect you to show work on how you simplified. So if you're just using the derivative calculator and coming up with answers, right, you're not really doing calculus, you're just plugging into a calculator. So I do expect to see a bunch of work like this right here. And if you did do some simplification, right, I need to know, how did you do that? How did you get from here to here? So please practice writing your work down.